Hello, everybody, and thank you for inviting me. Last time I gave a talk, it was in the small building you were in. I spoke to the math department before, but this is a little different. Okay. So what I'm going to talk about here is two aspects of data complexity that really have been on my mind for many years. If I can turn my slides, like in particular, what I'm going to talk about is multimodality, something that you all know about, as well as subclass mix, which is a continuation of multimodality, which appears when you do classification. What I'll do is discuss their effects and then show how, using the same principle for all the studies that I'm going to talk about, use the same very simple divide and conquer principle, show how we can harness that difficulty to improve classification performance. So as everybody knows here, data analysis can be quite powerful. And when we have a single distribution, well, we have a lot of tools to understand the data we're looking at. We can take the mean, the variance, look at the skewness, the kurtosis, as well as the modality. This last one, the modality, looking at whether the distribution is unimodal, bimodal, or multimodal, is what I'm interested in here. So that's one thing. And the way I represent it, so I'm not a statistician, so I have lots of pictures and lots of conceptual things, not many formulas. But so the way I see it here is that, well, we may have a distribution that's a little bit, that looks complex. If I wanted to model this, it looks complex. But if you decompose it into a bunch of different modalities, you have three pretty easy distributions to work with. So that's the first aspect. But now moving to two distributions instead of one, what you have is that if both distributions are multimodal, then maybe they will mix somehow. And that's what I call the subclass mix problem. So I started working on this, a long time ago, 20 or so years ago. And the first thing I did was to look at data sets. So for example, at the time, the sonar data from UCI was quite popular. Things have changed since then, but that's one I worked on. And I decided to plot, to see what I could see in it. So I took the first two components, principal components, and then I plotted it and I did some basic clustering, using some graph theory stuff. And what I found is that the distributions were pretty much intertwined, like definitely multimodal and intertwined. In that, what you see here, I think the black triangles are the mines, the white circles are rocks, and this is whatever, like there's a sonar and whatever's reflected is the measurements that we have in the data set. And we see that, for example, here we have a cluster of mines, but in the middle here we have a very small cluster of rocks, and then another cluster of mines. And so we have that kind of intertwining. That's what I call intertwining, where you have things in between the classes, like separation between the subclasses. So from this, like I saw that this was a problem, and I created a few stylized data sets just to be able to work with. And I show you two examples of one. So one that I worked for a lot for a while was the one on the right here. And the way I got to it is by truly taking the means of each of the subclusters that I had learned, mines or rocks, and then looked, created something that was a little bit, more regular, but similar, with intertwining of the positive class, the negative class, positive, and so on. Another stylized case that I like to work on a lot, and I like these data sets because they really help me understand what's going on with the different classifiers. Another one that I did was this time univariate. I had only one feature, and I lost my cursor. Oh, here it is. I created domains of different degrees of complexity. And by complexity, I mean, well, if I could put the threshold at 0.5 and say everything on the left is negative, everything on the right is positive, and I have a linear discrimination, right? Like I can do linear discrimination on it. Then I made it more difficult by divided it into 4 parts, minus, plus, minus, plus, and that's a second degree of difficulty. The one you see here is a third level of complexity where it's divided into 8, and then I moved to 16 and 32 as well. And I played with that, trying to see to what extent that intertwining between class distributions made, what effect it had on the classifiers we were using. And then I also looked at those in different situations. So these are the two main aspects of data complexity that I've always been very interested in. There are others, though. An important one, which I've never worked on for some reason, it's not one that spoke to me, but it's a really interesting one. It's the class overlap, right? In all my domains, as you could see, the positives are the positive, the negative are the negatives. They do not. There is no gray zone in between the two. Other people have looked at my work and then added the class overlap and got very interesting work as well. But as I say, I have to confess, that's one I haven't worked on. The other ones I have worked on, and I will talk about in this talk a little bit. So class imbalances, looking in particular at between and within class imbalances, small disjuncts, outliers, representational issues. So looking, moving away from one or two featured domains, and those nice stylized one, but looking at real domains where we may have some irrelevant features or redundancy, as well as questions of feature representativeness. And I looked at data scarcity in general as well. And then there are many more aspects of data set complexity that I'm not even thinking of. But once again, the two main aspects I'm going to look at here are multimodality and then the subclass mix problem, where there's that intertwining. And I'll talk about some other things as well. So here is how the talk is going to go. I don't know, I may have a little bit too much, so we'll see how it goes. I was hoping to present 4 different studies that I did over the whole span of my career, really, the past 20 years. The first one looks at how we can harness the multimodality and the subclass mix effect in a particular case in the class imbalance problem. Then a second one is how to look at multimodality in particular to see if we can improve binary classification. The third one is how to harness the subclass mix problem this time, and this time to deal with multi-class classification instead of simply binary classification. And in the last instance, I'll look at one class classification and then see what we can do about multimodality to improve on that. And there'll be a little part on feature selection as well. Now, if you look at the dates, it looks like I didn't do anything for 10 years, right? Like between 2004 and 2015. And when I realized that, I said, oh, really? Wow, did I sleep for 10 years? No, not quite. I guess I will, justify myself here. Now, what I did in these 10 years were really looking at other issues. I mean, these were always in the back of my mind, but I looked at issues such as, I think, machine learning evaluation was an important one. And that's one that I'm actually revisiting at this point with Zois. Actually, we just got a book contract to revisit the old book that I had done with a former author. And another big thing I was doing in those 10 years instead of simply sleeping was also working on more practical problems. And all that work that I did on security was done in that years. Here, what I'm talking about most is really conceptual, not very applied. Maybe at the end, you'll see some applied stuff. But okay, so I feel better. I felt better after I realized that I was not just idle. In all the studies that I'm going to show you, I applied this very the same simple divide and the same simple divide and conquer principle. So assume you are trying to classify the red class versus the blue class. All we did in the first step, at least, was we are going to divide, things into subclusters, and the subclusters are either reddish or bluish. Okay, we still have the classes. And after we do this division, we do something. Okay, but it's always that same idea. Instead of dealing with a complicated distribution, look at it in a simpler way and then try to see what that gives you. So in the first study, where I worked on the class imbalance data, I'm going to discuss what we did in this respect. But before I do so, because either the class imbalance problem is not a problem that is looked at much in data science or in math, or maybe it's looked at but with different words, and that I would be interested in finding out. I'd like to explain a little bit what I mean by class imbalance problem and what the effect of multimodality and subclass mix has caused. So in the class imbalance problem, the way it's defined in the machine learning that comes from the AI community is really, let's say that you have a two-class problem, positive and negative, and you have a lot of instances of one class and very few instances of the other. So the difference, there's a big ratio of difference between the two classes. When this happens, classifiers tend to say, let's say that your large class was the positive one, it seems to say everything is positive and believes that it's doing very well because its accuracy is very high or something. In reality, we're not interested in a classifier that says everything's positive. We're interested in a classifier that may make some mistakes on the large class, but manages to get something interesting to say about the small class. So that problem occurs a lot. And in 2002, I did a study to try to see what the factors are that cause problems in class imbalance cases. So I looked at 3 factors in particular. And again, I'm looking for my cursor. Here it is. So one of them was domain complexity. And for that, I used that backbone I showed you before, where here you have an example of domain complexity 3. The way this is shown in the graphs that I show you on top are each level of difficulty is a bunch of columns. Okay, so here you have 1, 2, 3 written in very small letters that you cannot read, or they're not letters, they are numbers. These have to do with the complexity. The size, how much data I had in my domain that I was classifying. And the third one is how imbalanced my data is. And I had different ratios. So the size are shown in each graph. Each graph is a different size, where size 1 is small, size 5 is large. And I don't remember, I don't have the exact numbers, but they are in the paper that's above. And then the way I showed degrees of imbalances is backward. For some reason, I decided that the first column in every case was the most imbalanced. And the other columns, they went from most imbalanced to less imbalanced as we went down. And the results I showed, I found by running classifier. So here, this is probably a decision tree. What I found is that several things of interest. Number one, in all cases, if my domain is linearly separable, right? So that's my simplest case when I just have 0.5, everything is below 0.5 is negative, everything above 0.5 is positive. No matter how imbalanced and no matter how small my domain is, that's not a problem, right? What I'm showing here are error rates, I think, corrected error rates, meaning that even though my training data is imbalanced, my testing data is balanced. Okay, so we don't, we see exactly what we have. We don't have to go to ROC analysis to see it. So no problem at all, no matter what, no matter how imbalanced, how small. Like the worst case would be probably the most imbalanced, the smallest. If it's linearly separable, forget about the class imbalance problem. It's not there. What we found as well is that as we increase the imbalance and the complexity of the domain, so let's start with the complexity of the domain. As I said, it increases more and more as I go along in those clusters of columns. So the more complex the domain, the more sensitive it is to class imbalance, for large levels of imbalances to less large ones. And it's worse in the case where the domain is small. It gets a little bit better as the domain gets, larger. So for example, in size 5, a largest case, only in the most complex domains and when I have a very high level of imbalance, level of imbalance 1 or 2, does my classifier suffer. Otherwise, it doesn't. Okay, so anyway, this was a premise to introduce you to the class imbalance in case you didn't know it, and to talk about how the class imbalance hurts classification. tasks. But it's not really what I wanted to talk about here, because what I want to talk about is what we did in terms of harnessing the multimodality and subclass mix effects in class imbalances. So the premise is that we have different ways of dealing with class imbalances, but I felt maybe we can, I don't know if it does better in every case, but maybe we can try something else at least. So how do we deal with class imbalance problems? Well, we can do random oversampling. We oversample, at random, we pick examples from the small class and we make the small class bigger. Or random, that's a problem usually because it overfits the data. Random undersampling, which tends to work better. Then there is SMOTE, which is a particular method that will oversample, but it doesn't repeat exactly the data. It basically takes the convex hull of all your small data set, the small class, and then picks points in between. You can also change the classifier. You can rebalance the cost. Like every instance will have a different cost depending on which class it belongs to, and the cost is proportional to the amount of imbalance. And what you can do is, play with those costs in your classifier. Or you can also do one class learning. Forget that you have two classes, work on only one. This way, imbalance means nothing, basically. It's just a different problem. So what I thought, or what in this work is that, well, maybe what we could do is do some sort of oversampling, random oversampling or random undersampling, but do it a little bit more intelligently. And one thing I figured is that when you have a problem, and let's take this simple classifying vowels versus consonants, you have two different kinds of imbalances. On the one hand, you have the between class imbalances. So these are the that's the class imbalance I described before, right? I said, well, you have lots of data of one kind, very few data of the other ones. Well, in English, we have, or in most languages, we have very few vowels and lots of consonants, right? So there is an imbalance there. But then there's also another problem, which is the within class imbalance problem. And that is something like what you see here in my blue. So the blue cases are I have the consonants there. There are not many Fs, if you look at frequency, how frequent those different letters are. That's what I try to show by those different sizes. It's not fully accurate, but F is not a letter that you use as much as R or M in English. So within consonants, you do have different degrees of balance, right? Maybe the F, if you take all the consonants and you try to classify them, maybe the Fs won't be considered as that important and they'll just be forgotten by the classifier. So I was thinking that that could be a problem. And for that reason, we designed a solution to that. The first step of that solution is to use, what I showed you before, a clustering algorithm that will be run on each class to subdivide the multimodal data into separate distributions, and then simply oversample or undersample proportionately to each cluster, so that in the end, you'd have an approximate between class as well as within class balance. Because the danger, if I go back to here, what would happen if I just did random oversampling? So let's say that, let's say that I'm here and I have to oversample the red class. Well, because U's are not very frequent, if I randomly pick data, I'll be picking a lot of A's and a lot of I's, but not very many U's, okay? So the problem may become even worse in some way because I need to pick a lot of those to make it as big as the blue class where I have lots of consonants, but my U's will become relatively smaller and smaller, and there's no chance I'll recognize them. So here the idea was to try to boost the U's a little bit. So, we can do what I just, let me illustrate what I mean by this. So with the first class, the first step would be for each class to do what I showed you before. You have one class, you subdivide it into, clusters. And then the second step is to, let's say, oversample. So you see the one that has the most points here is the red class. That greenish thing has only 6 points. So you add points so that it has approximately the same number as the red ones. And similarly with the yellow, okay? Or you can do the opposite. You can undersample everything. right? So the smallest class was this one, the one with the 6. So you undersample the red class and you undersample the yellow. They're not class, they are subclasses. So doing that, and the third step, as I said, was to classify the new data set. So I did some experiments with that. I mean, I in some cases, in that paper, I alone, in the other one with other people. Oh no, even that one was with other people, I think. So I'll keep on using we because most of the work was done with others. So when I look at the letter classification experiment, what we found is that, maybe we'll look at the F measure, which is like I have precision recall and F measure. What we found is that if we did simply blind resampling, we did no better than no resampling at all on this particular case. But if we did what I called guided resampling, which is that resampling but taking into consideration the frequency of the subclasses, then we saw an improvement of, we get 2.919. For some strange reason, in this particular experiments, the first time I used only the number of clusters was known. In the second case, I actually knew the clusters. I didn't do as well. So that tells me something interesting, that perhaps we should let the data organize itself, let an unsupervised learner cluster it instead of using knowledge on this. But that was only one experiment. 3 or 4 years later, we looked at this again and then applied it to different domains. So here I show 3 different domains. On top, you have the cancer, breast cancer. Then you have the diabetes domain, all from UCI. The third one is it's not from UCI, actually. I think it was a proprietary data set. What you find in all cases, we compared a bunch of different classifiers. On the left, you see C4.5, a decision tree. On the right, you see a neural network, like backpropagation, like MLP. And I have also, when I have 2 different settings, one of them has a small amount of data and the other one has a larger one. And then these are all the different classifiers we use. So cost modification, nothing, cost modification, pruning the small disjuncts. Small disjuncts, by the way, are subclasses, subclusters that are very small. It's almost like outliers, but outliers are only 1 point, whereas the subdisjuncts are, subclusters of that. So a bit bigger than an outlier. And again, several methods. The thing to know is that the last one is ours. So in the breast cancer, you see that what I proposed did better, at least in the small case when we don't have much data. When we have more data, it does better still, but it is not, the difference between, I don't know which one that is not that great. And that's for decision trees. Neural networks seem to do a lot better, at least when we have lots of data. Still not so well when we have less data. And again, our method seems to work better. The same kind of thing is seen on the PIMA diabetes data set. And then to a certain extent, but not a great extent, on the extra domain. So anyway, I'm not saying this is the best method that was ever invented. I'm just saying it is a way of seeing the data, the way of seeing the world and resampling that can be helpful, at least in certain cases. Okay, so that was the first study. In the second study, are there any questions, by the way, or should I keep everything to the end? No questions? Okay.
You can ask a quick question.
Yeah, we can have the questions at the end.
Oh, sorry.
Oh, at the end, you prefer the end. Okay. All right.
Sorry, can I just interrupt? I do have one. This will help through the whole thing for me. Just when you talk about different sizes of data sets, like what ranges are you talking about? Because this may be different depending on your discipline.
Okay, we were in the early 2000s, so we're not talking about probably the kind of data sets you're looking at. Like it's probably in the hundreds, versus, and then the low hundreds versus the 500s. Okay. But again, a lot of things are relative. So in large data sets, it's possible. That's a question I asked at the end, actually. Maybe when you have lots of data, these problems are not there anymore, although I suspect they still are. But I'd be interested in talking to you about this.
Great, thanks.
Does that answer? Okay.
May I ask a question, please?
Of course, yes.
Yeah. So recently I've heard about these things called generalized adversarial networks,
Yes, of course. Yeah.
where there is a discriminator and a detector and a detector. So what happens is that, there's one algorithm that's trying to generate fake data
Mhm.
to cheat the discriminator, and the discriminator's job is to catch the fake data.
Mhm.
So it's a minimax problem. So is it something similar to that SMOTE that you're talking about? And how do you think that compares with these algorithms that we are talking about here?
So it's a very good question. What you're talking, the way again could be used is actually to generate data. So here I'm talking about a classifier that simply does, like, it's not generative. I'm talking about k nearest neighbors, about CART, about, those kinds of classifiers, also about discriminative, neural networks like multi-layer perceptrons and things like that, and deep learning as well. I'm talking about those kinds of classifiers. But what's interesting about GANs is that instead of randomly sampling the data, when I don't have enough data, I'm talking about randomly sampling the data. GANs do something more interesting because they create fake data that can be used for resampling. So
Right. So that is similar to SMOTE, right?
It's similar to what?
The SMOTE that you were talking about,
yes.
where it's generating the elements in the convex hull.
Exactly. It's similar to SMOTE. It has been tried. I mean, I have a PhD student who did his thesis not using GANs, but using autoencoders to generate the fake data. And he showed that in certain cases, he was actually doing better than SMOTE, because he was able to learn something better than just the convex hull. But definitely GANs can be used for that. And yes, comparing, seeing if they do as well and what can be done. And if we need to do more than what GANs or autoencoders do is interesting. In fact, we're trying to put together a workshop that would talk about those old traditional machine learning methods that are the ones I'm talking about here, and then the deep learning methods, and holding a workshop to have discussions about whether there's a need to combine those two ideas.
Oh, thank you so much. Sorry to interrupt you.
Oh, no, my pleasure, on the contrary. Okay, so in the second study, I'm not going to talk about class imbalances here, but I'm simply going to talk about binary classification and whether that little trick, very simple divide and conquer trick, can be used to improve how we do binary classification. And the observation starts from realizing that when we have labels, it's great to have labels for our data in a classification problem, but those labels may be a little too constraining in a sense, because maybe we are putting very different things. Let's say we have a cancer data set, and maybe we're mixing very different kinds of cancers in that same data set, like we did with the vowels or the consonants, for example, which is what I'm showing like here, right? If we look at these letters again, this, an R and an A actually look very similar, as do P and F. They look similar to the R's. So in the input space, R and A are very close, but I'm calling them different. I'm forcing a boundary between them because one is a consonant, the other one is a vowel. At the same time, R and M don't look very, very similar. That's why I put them far away in space. And yet I'm forcing those to be called the same thing. So I'm creating these very difficult problems where naturally R and A would be, close to each other. Maybe U and V would be close to each other. I and L, if they are written in some ways, would be close to each other. And yet I'm forcing boundaries between them and forcing different things like an I and a U to be close to each other. So based on that observation, I was wondering, well, can we use that divide and conquer type of thing and subdivide our data into lots of classes and say, instead of saying we're going to do vowels versus consonants, we're going to do P versus R versus U versus A, you know, doing a multi-class classification problem. And maybe that will simplify things. So that's what I did. And I compared a few things, and I apologize because this was done over several years. It was not the same study. I'm just putting them all together in this talk, but you know, a nice thing would be to have all these studies put together. So I'm comparing different classifiers from the ones I used before. This time I'm using C5.0 and a boosted version of C5.0. C5.0 is again a decision tree, the next version of C4.5, but it never really flew somehow, but I used it in some part of my life, I used it. So what I show in these results are, in the first two columns here, the results using boosting and non-boosting here and then boosting, but not using the trick I just showed you. And then I looked at using the trick, so doing multi-class classification with boosting and no boosting. And in addition, I have different versions. Since I use I use unsupervised learning at first to divide the data. So I have different versions of my clustering. So I make an ensemble of that, and then I put them together, like I let them vote. But the votes are either weighted or not weighted, given the certainty of the classification I get. So that's what I show here. And I show that depending, you know, sometimes in this case, for example, on the Haberman data set, there's a small improvement if I use non-weighted, non-boosted ensembles of this sort. So the results are not very good on Haberman. They are very bad on ionosphere. In fact, I'm better off doing nothing. But on the last three domains, it actually improves, because the best I could get doing nothing special was the boosting here. If I use some of my combination, the boosted ones, I lose, you know, a couple of percent. This is the error I'm showing. So the lower results are best. And this is the improvement you see. So on the last three data set, I get some improvement from that. So again, are these the best results you'll ever see? Probably not, but I wanted to show that this idea can help. Is there anything else I wanted to say on this? No, I don't think so. So let me move. Again, I'm happy to take questions unless this makes things too long. No? Okay. So the third study that I want to talk about, this is the one, since I'm talking to mathematicians, I thought I'd include it because I was so glad to come up with a formula, actually, something that looks mathematical. All the rest of my work is always pretty pictures and stuff, very heuristic. So here you'll see a formula soon. In that third study, what I did here was that actually it addresses a weakness from the previous study. Because, well, maybe it's a good idea to subdivide my consonants into specific, letters to make the problem easier. On the other hand, using a multi-class classifier is not something that does very well. It's much easier to do binary classification than to do multi-class classification. And in addition, not every classifier is really naturally able to classify into multi-classes. That's the case, for example, of support vector machines. So there is one method that I've always liked. I had it on my, it's an old paper that I even had on my comprehensive exam. And that's error correcting output codes. It's a very powerful method that combines binary classifiers to produce a multi-class classifier. So the fact that I'm going to talk about this study after the previous one is relevant in two ways. Number one, I will show you what I did with the ECOX, which is similar to using that same divide and conquer thing. But in addition, maybe I could improve the second study by using ECOX. Since I'm doing multi-class classification, maybe I could use ECOX on top of them to get better multi-class classification. But anyway, you probably don't know what ECOX are, or at least in this context. And I'm going to start by presenting it to you. before I do so, what I want to do is tell you that the main component of ECOGs is the design of the coding matrix. And that coding matrix is how you do a particular division that you'll understand in a second. And the thing to remember also is that there are two ways of designing that coding matrix. One is information theoretic, and the other one is a data-driven way. And I use the data-driven way, and you'll see very soon what I did on it. So in this study, what we propose to do is to use a data-driven approach to design the coding matrix. And that method will take into consideration both the subclass mix problem as well as the class imbalance problem. So now let me talk about ECOGs. So, and it's not my work. This is work by Dietrich and his PhD student a long, long time ago in 1995. Assume that you have a multi-class classification problem, say a 6-class problem, like you see here. What ECOGs does, like what that method does, is to decompose the problem into a bunch of different binary problems. So you have BD1, BD2, the different binary decompositions. And how does it decompose it? It's saying, well, let's assume that if you are part of, let's look at BD1, and it says, well, anything that's in, if you have an example that's in class 1, or in class 3, or in class 4, well, relabel it and call it class 1. And then everything else call class 0. So you're creating a new binary problem where you know, class 1, class 3, class 4 are bunched together. So it's exactly the opposite of what I was doing, by the way, right? Instead of bunching those sets, those classes together, I was trying to unbunch them. This method bunches them together, but it does it in many different ways, right? So that you have a sort of a code word that tells you what the classification is. So what happens? You create those problems and you relabel them, right, as binary problems. And then you train on your data and you get an error. You know, every new example that comes will be classified by each of those binary classifiers. And that you'll see here. So let's say you have a new instance that comes, some example. And this example was classified as 0 by the first classifier, by 1 as 1 by the second, as 2 as 1 by the third, 0, 0, 1, 1. What you do when you have this vector is that you take the Hamming distance of this vector to all the code words that you have to see which one it is closest to. All right. So I put the Hamming distances here, and this one we see is 1. Why is it 1? Because here you have 0. You expected a 0, but you had a 1. So it's 1 error. And then here you have 1 and 1, 0, 0, 0, you know, so all the rest is the same. So you made only one mistake, and therefore the Hamming distance is 1. It is 4 here because you made 4 different mistakes if you look through it. And of course, you could choose the one with the smallest distance, and you say, oh, that distance was an instance of class 2. So it's a very clever method and robust in some way. And now maybe you can see why I was talking about the coding matrix. This matrix that you see here in terms of 0 and 1, zeros and 1, is what we call the coding matrix. The way it was designed in the original paper was using an information theoretic principle, and that's where the name error correcting code comes from. The idea was to get each of these words, each of these coding words, as far away from each other, so that when a new instance came, you know, it would be as far as possible, so that the one it's closest to is, you know, the most likely one. Now, people have done work on designing this matrix in a more data-driven fashion and getting better results than the original information theoretic way. So that's the direction I took. But what I did in this work is that I realized, I went back to my, you know, my interest from before, which I already talked about when I talked about study 1 and 2. What I wondered was, when I decompose these, You know, when I say class 1, 3, and 4 will be class 1, and class 2, 5, and 6 will be class 0, am I helping the classifier or am I making its life harder? You know, on one hand, when I have, let's say here, I have 9 different classes, okay? If I say, well, all these X's here are one class and the zeros another class, well, if I do that, if these are the classes that are bunched together and these are the other classes that are bunched together, I'm creating a very easy problem. So my classifiers will do well. The problem may be slightly imbalanced in that I'll probably have, you know, more data on the X side than on the O side. And maybe I'll deal with that soon. But if on the other hand, my decomposition is such that I need 4 different lines to separate between them, I'm dealing with a very hard problem. And that's not something desirable by the same token here. But on the other hand, this one is balanced. This one is very simple, right? It's easy to divide, take away X from the rest, but it's highly imbalanced. So I decided to search for coding matrices. So search through the space of all coding matrices to look for ideal ones, but at the same time, coding matrices that would yield easier problems as well as a balanced one. So this is where my, you know, my math part comes, because that big formula is the kind of thing that I stay away from usually, but here I did it. So we proposed a method in which we decided to use a search algorithm, a genetic algorithm actually, which is a, you know, like a randomized algorithm that will go through different matrices and change. So it's something based on genetics where you have a crossover and mutation. You know, we sort of copy the way, I guess, reproduction happens, but it's very, very general. So we search the space that way. And the way we guide the search is by having a fitness function. And what we did is that in the fitness function, we wanted to make sure that we had a way to compute how difficult our classifier, our domain was going to be for a classifier. To do that, we created the separability criterion between the positive and the negative class. And this is what is expressed here. So basically the method works by, first of all, using that same idea of divide and conquer, we cluster the data into subconcepts. And then we try to see how much intertwining there is between those different subconcepts. And that amount is sort of calculated here. So here, what do we have? We have C++, I'm showing it for the positive class. We also do the same thing for the negative class. So C plus I is a cluster. It's the center of a subcluster that's of class plus, of a positive one. And then D is a distance between, it's the distance measure between different cluster centers. So what we are saying, I is the indicator function. What we are saying here is, for going through all the different clusters in the 2 classes, okay, and 2 is the negative class and 1 is the positive class, so we have a loop going through everything, we're going to count 1 every time the distance between 2 positive centers is larger than the distance between a positive and a negative one. Okay, and then we normalize the whole thing. So to give you an example, here's an illustration. What I'm showing here is if everything is on to simplify it, if everything is on a column, no matter how far it is, I'm saying it's a short distance. It's a distance of 1. Okay, so this plus and that plus are at a distance 1 from each other, let's assume. And these 2 minuses are a distance 1 from each other, but there's a distance 2 between the plus and the minus. And by the same token here in this second domain, this plus and this minus and this plus and this minus are all at a distance 1, but this plus and this plus is at a distance 2. So in the first domain, my separability criterion would give us a value 0, because everything plus, right, is at a smaller distance than any distance between plus and minus. On the left, however, and I show this on the other one, we find the separability criterion we get is 1 of 1/3. And my next slide explains why. It's a little confusing. I mean, a little dirty, I guess, but I'll go back to the first slide if it is too much. Why is it so? Because as you see here, all the things on this line are value 1 in terms of distance, and everything going from one line to the other is distance 2. So we take the first plus, okay, and we say, well, how many times do I have a value, like a distance between a plus and a minus that's smaller than between a plus and a plus? Well, there's this one, this plus to this minus is a 1. This plus to this minus is a 1, whereas this plus to this plus is a 2, right? So on two occasions, I have that problem. Then we do the same thing for the plus, the second plus on the left, and we find that again, it's 2. Then we take the plus on the right, and again, for the same, symmetrical reasons, it's 2 again. And then we had the indicator function called 18 times, so we get 6/18 or 1/3. So having this separability, so really this function that this separability criterion is a criterion that tells us how difficult is the domain we're trying to classify. So we wanted to enter that in our fitness function, which is what we did here. We took the minimum that we got when we looked at the separability of the plus and the separability of the minus. And then we looked at different sizes of matrices because, the genetic algorithm will try lots of different matrices. So this is the fitness function that we came up with, and using that algorithm, we generated some different coding matrices. Now, in addition, I mentioned that not only were we going to look at the difficulty of the domain, but we were also going to look at whether it was balanced or not. So once we looked at that, we saw the balance. We used random undersampling or SMOTE, which again are probably the two simplest and best ways to deal with the class imbalance. And after doing that, we tested our approach. So we use 4 UCI domains as well as a domain of automatic, like 2-digit recognition. That's for, on checks, for example, to have those bank machines read your check. That is a useful problem. And we used a bunch of classifiers. So in this case, we use CART and SVM, and these are the different parameters and whatever testing regimen that we did. And what we found is that the method was helpful. So we're comparing CART alone, AdaBoost alone, and DCOC is the data-driven, the best data-driven method that they, that we had at this point in 2015. And we compared how we were doing on this, and there was some improvement in all cases, actually on the letter, on all these domains, there seems to be improvement. I highlighted the best improvement. This is using decision trees. We also saw improvements using support vector machines. And so there was something to getting to know what the difficulty of the problem was, and trying to use it, not just do a data-driven coding of that matrix blindly. I don't know, do I have enough time to continue and go into the 4th study, or am I talking too much?
You have a few more minutes.
Okay, so I'll try to do this quickly.
Okay.
Thank you. So in the 4th study, what we're doing now is looking at the problem of one-class classification. So as I said, if you have a class imbalance problem, one solution is to, instead of learning to discriminate between the two classes, you can drop one class altogether and say, well, what I'm going to try to do is recognize instances of the class I'm training on, right? So it's more of trying to to understand what your class is, what the class you're training on is, and then rejecting things that don't match this. What we did here is that we noticed that if the class, so now we are learning from a single class, the background class. If that class is too complex for a single learner, it may be useful to use that same trick that I've been using all my career, right? My divide and conquer strategy, saying, well, instead of throwing my one class learning system on my data distribution of one class, I will simplify my data distribution by using unsupervised learning first, and then using a one class approach on each of those subclusters. So this is the approach. First, we divide the data into subclusters. In my PhD student's thesis, we had 3 different cases. Sometimes we had full knowledge of the clusters. Sometimes we had only partial knowledge, and sometimes we had no domain knowledge at all. What I'm talking about here is the no domain knowledge at all, where we have to rely on unsupervised learning to form those clusters. Then we trained a distinct one class classifier on each subcluster. And then depending on how close we had the data, and then we see which one to direct. It was like a stacking problem, basically, where we decide which subcluster we're going to use to classify. A little bit later, I had a visitor. So this is work that was actually done at AU at last. So I had a visitor who came, and she decided to improve the methods in 2 different ways. First of all, she said, well, maybe the clusters that we learned a priori are inadequate. So she wanted to use a measure of cohesiveness to consolidate the results of the clustering systems, and this way avoid small disjuncts. The idea was that if our clusters were too small, maybe we should merge them with bigger clusters, and this way we'll do better. She called that cluster updating. And another thing she did, which I thought was really useful, something that bothered me about the first work, is that the way in which we decided how to combine the results. Like in the first method, the one I showed you here, we said, we'll choose one of those 4, let's say, OCC1, OCC2, one of them will be chosen. But maybe we can do better if we vote, right? So here, she tried 3 different voting methods. One of them, A3 is the one we had. Choose the vote of the model that corresponds to the example we're trying to classify. And then A1 or A2 are one where we consider different submodels. A2 considers the vote of all the models in the system, and A1 takes only the 3 clusters closest to the testing instance. So doing that, before I talk about this, in this case, we used a more practical domain. We were doing host-based intrusion detection, and we use those are Australian data sets that are, they replaced the DARPA 1999 data sets that have been used and overused. So these are more modern. So that's the data we looked at. I'm showing the principal component just to show you what they look like. What you're seeing here is the background. You don't see the attacks, okay? But you see that it's highly multimodal again. So the trick may help. That was the idea here. These are the results we obtained. The one class classifiers we use, we use only one here, is isolation forest, and we report the F1 measure. So what I show here is the SOCC is without cluster updating, but the schemes are A1, A2, A3. And here it's SOCC with cluster updating, and again, A1, A2, A3. So A3 was the original method, and original is do nothing, just use one isolation forest on the whole data set. So what we find in general, if you look at this result, you'll see that the ensemble scheme that addresses multimodality is helpful, and that in terms of which combination works best, it's A2. A2 was the one that used, I forgot, it's the one that uses the votes of all the models in the system. I forgot if they were weighted or not. I'd have to look at the paper again. I assume they were weighted, but I'm not sure, by distance maybe. So cluster updating helps a little bit, but not much really. So the big deal was to combine everything and not just to use stacking, which would use only one thing. I have one last thing to talk about. It is using in the same context of one-class learning, but this time doing feature selection. In many domains, when you do binary classification or multi-class classification, it's common, like people know that doing feature selection or feature, change feature extraction, like lots of different data transformations can be useful. In one-class classification, we'd love to do it as well. The problem is that such methods do not necessarily work. And why? Because the feature selection methods often use the class, the known class, and finds some sort of relevance. Like you look at the attributes relevance with respect to the class, and the class is known. If you're in one-class learning, the class is known, but there's only one. So there is no real ways to know which attributes or which features will be better. So the idea that we had here is, again, to use our divide and conquer strategy, cluster our data, create pseudo classes from that, and then use the traditional feature selection methods. And then after that, do our one-class learning. So this is the overall scheme. We have the training set. We divide it into clusters. We don't know the value of k, so we iterate over different values. Then once we have our clusters, which are our pseudo classes, we recreate the domain here with our pseudo labels. We pass that through existing feature selection algorithms like gain ratio or symmetric uncertainty, local correlation metric. It could be any others as well. We rank the features according to them, and then we take the mean rank, we select them, and we evaluate using an internal value, of our clustering. I mean, one-class learning is a little bit like clustering, so we use that, and then we iterate again, and finally converge on an optimal set of features. Once we have these features, we compared our results. So we use 3 different one-class classifiers this time: one-class SVM, isolation forest, and the autoencoder. And what we found, what I show on top are the AUC results, at the bottom are the F measure results. We find that in terms of AUC, so wait a second, our method is the SCFS method. We have 3 different domains here. They were all like those intrusion detection domains, but 3 separate ones. And FFSOC is the only one filter approach for one-class feature selection that we could find. So we find that in some data sets, in this one, we did a bit better with a couple of one-class learners, but on the second one, FFSOC beat us by quite a lot, at least according to the AUC. On the third domain, again, we seem to be doing slightly better. If we look at the F measure, we seem to be doing better more generally. Anyway, there is good and bad in both, but there could be, in certain cases, there could be some advantage to doing this. All right, so I'm done now. Let me just conclude quickly. What we've done is looked at the multi-modality and subclass mix problems. And I show that it can cause some difficulties, especially if we look at binary classification, multi-class classification, one-class classification. And we found that the problems were particularly acute in cases like class imbalances, small disjunct, general data scarcity. So that's what I did in the talk. In terms of future work, well, since I'm talking to you guys, like people in statistics and in math, it would be great to formalize all these heuristic methods that I used here into some more rigorous statistically based procedures. Also, what I did is present different methods, but I think that combining at least some of them could be useful. So maybe if we could have like a one system, much more formal system with parameters to control how much of what method we use, That would be nice also. So I'm thinking of, thesis topics if any students are here looking into this. Now, as one of the questions that I had before, suggested, does deep learning erase all these things? Like, do we not need any of the things I talked about here because of deep learning? I don't think so, because I don't think that deep learning is is the answer to everything. There's still many problems that don't use deep learning. But even in deep learning, I suspect I've seen papers on class imbalances, for example, in the case of deep learning. And then another thing is that a lot of the work I did here could be quite time consuming. So transforming these algorithms into parallel implementations would be useful. And that's it. So I don't know if we have time for questions, but I'll be happy to take.
Thank you very much, Nathalie.
Thank you.
Any questions for Nathalie?
May I ask a question, please?
Yes, of course.
Yeah. So you were talking in your last segment in item 4 about feature selection.
Mm-hmm.
So we are talking about imbalanced data sets, etc. So one of the problems that we face is that the number of observations, the n, the number of rows, is much smaller than the number of columns, p. P is much, much greater than n.
Mm-hmm.
So in such a situation, even if you're trying to, let us say take SM or TS mode, for example, and you're able to generate synthetic data.
Mm-hmm.
Now it turns out that for all our upstream machine learning algorithms, let's take the simple example of logistic regression. The P greater than N is a major problem in spite of oversampling. How do these methods deal with when N is equal to P or when P is greater than N on the classification side of the fence?
So these methods are meant to reduce P, right?
I thought we were oversampling. I thought the methods were to increase N. We didn't address the issue of P, right?
Okay, so you're talking about the class imbalance. Okay, here, I mean, are you talking in general or are you talking about in my study?
In your studies, you're oversampling to get an inflated N, and now you got a P problem, which is greater than N. So what effect does it have on the classification like SVM or CART or C 4.5, any of those values?
So that's a good point, but that's not what I looked at actually. I mean, each of the 4 studies were separate, right? And in the last study, I was looking at one class learning. So there's no oversampling at all in there. It's throwing out the small class instead of doing that. So I was looking at feature selection in the case of one class learning. Now your question maybe refers to my first study when I was talking about oversampling. And
yeah.
It is a good question. So you're right that if we add data, then we don't have the curse of dimensionality. I mean, it depends how much we add, I suppose, but maybe we can move away from the curse of dimensionality. I don't think it really helps, because what is known is that when you oversample, at least at random you overfit for sure. So you don't get away from the curse of dimensionality. If you use SMOTE or other methods that generate data very close, maybe you don't overfit as much. I don't know the answer to your question. It's a great question, but my guess is that you'll probably end up overfitting as well, but I don't know.
Yeah, okay.
Yeah.
All right, thank you.
Okay.
Any other questions for Nathalie? Okay, well, thank you very much, Nathalie.
Okay, well, thank you.
Great talk. Thank you.
Okay, thank you.
Thank you. Thanks so much.
Okay, yeah, bye-bye.